So, Andrea, you are ready?
Yes.
Okay, I think I can start. So let's welcome to this afternoon session and the last session of this workshop. And the first speaker is Andrea Sfecci from the Università degli Studi di Trieste, and he will talk about the game of resonance existence results. Please.
Thank you so much. And just a few words in order to thank the organization, the organizer for giving me this opportunity of showing some existence result for scalar second order differential equations. And in the following, you will see some results that I have obtained in some recent paper and are linked in some sense with the main theme that you have seen in the seminar by Alessandro Fonda. So we are playing with the periodic problem and so the resonance phenomenon. So you will see some well-known name in the following slides. And let us go on. So in particular, we are going to consider this kind of nonlinearity. So it is very general at this moment. Some scalar second order differential equation. We ask for the moment T periodicity in the T variable and the continuity of F. Certainly it is quite restrictive in some sense that this assumption, usually you can treat the Kara-Theodori case, but since some of the paper I will quote are written in the Kara-Theodori setting and other in the continuous setting, so I prefer to maintain low level in some sense and ask simply the continuity of the nonlinearity. But you can do better in some sense with that regularity. So just an example, very simple example. You can consider the harmonic oscillator and perturb it with a periodic and bounded function. And it is a standard that is well known in literature that if you take the value lambda not belonging to the spectrum, so you can prove quite easily that there exists a periodic solution for the differential equation. And in particular, the main technique adopted is the one of, you can use, for example, the technique linked to the topological degree theory, for example. And it is also well known that if you assume that your value lambda, it belongs to the spectrum, you need some additional hypotheses. So in the literature, just you can find some possibility in order to treat this kind of problem, and you can find some condition which has the name you see here: Lazer-Leach condition, Landesman-Lazer condition, or Ahmad-Lazer-Pohl condition. Lazer is always present, and we will focus our attention on the Landesman-Lazer condition in what follows. And we see now a further generalization of this problem. You can consider the so-called asymmetric oscillator. So in some sense, you are asking that the restoring force is different when the displacement from the equilibrium position is positive or negative in some sense. And this problem was treated by Dancer and Fußcik. And so the spectrum, say, in this case, is called the Dancer-Fußcik spectrum. And this is the formula for the periodic Dancer-Fußcik spectrum. And as you can imagine, if you choose this couple not belonging to the Dancer-Fußcik spectrum, then using some, for example, topological degree argument, you can find the existence of a T-periodic solution. Instead, if you want to take a point of the Dancer-Fußcik spectrum, you have to ask some additional hypotheses, say, for example, the Landesman-Lazer condition. We will focus in particular on this kind of condition. But you can do more. And so in the literature, you can find the so-called jumping nonlinearities. So this is the fact, the reason for which the word jumping along resonance, along the Dancer-Fußc spectrum was this expression in the abstract of the seminar. And so you can ask some asymptotic condition on the function f. In this case, you can assume that there are 4 constants ruling the lim-inf and lim-sup. And so you can see that if all the constants are real, we assume that they are positive, because the case of negative constant is quite easy to be solved. The case of the 0 constant is quite delicate. You can do more when you are near 0 in some sense with the nonlinearity. So other techniques are can give more structure in some sense. You can get better result when you have some small constant in some sense. So we will focus our attention in some sense on large constant when we are away from the lower eigenvalue, say. And so the jumping nonlinearities has this kind of behavior. So we imagine that this nonlinearity oscillates in some sense when x goes to plus infinity or to minus infinity. So this is the natural generalization of the previous situation. So it is common to find in literature also situation like this one, where we substitute the constant function, the constant with some functions. And you can find in literature several situations that are treated when the lim-inf and the lim-sup of this ratio is controlled by some function. But we will not enter in these details. We maintain the argument in the constant case, say. So we will see the case where lim-inf and lim-sup are bounded between 2 constants. So it is natural to consider this set. So I have given this name resonance rectangle. In some sense, it represents the nonlinearity in the plane where you can draw the Dancer-Fußc spectrum, as we will see. So in this situation, you can prove that if R is bounded and there is no intersection between the resonance rectangle and the Dancer-Fußc spectrum, then you can find the periodic solution. And the argument is quite standard. You can use some topological degree argument, construct an homotopy, and then you can find the periodic solution. And as you can imagine, you can treat also the situation where there is an intersection, but the rectangle touch the Dancer-Fußc spectrum. So only the boundary, in particular 2 vertices of the rectangle, touch the curve of the Dancer-Fußc spectrum. And in this case, you need to ask more assumptions, and you can assume, for example, the Landesman and Lazer condition. So just to give an idea, let me collect some small bibliography, clearly the famous non-exhaustive bibliography. So you can add the paper quoted by Alessandro Fonda, by Alberto Boscagin in the previous seminar, and then we can try to complete, in some sense, this bibliography. But I will focus the attention on 4 papers. And the first, so there are also some papers, for example, the one by Van Ward, and if I well remember, the one by Fernandez and Zanolin, treating the case when we are between the axis and the first non-trivial curve of the Dancer-Fußc spectrum, because in this part you can have better result than one we have usually. So you can use lower and upper solution technique or variational methods. So you can obtain some result also using other kind of technique. But when you are between two subsequent curves of the Dancer-Fuќc spectrum, the topological degree theory works well in this part, say, of the plane. Let me just mention the fact that if you are at infinity, this is in some sense the zone of the Poincaré-Birkhoff theorem, in some sense, for those who are who plays with Poincaré-Birkhoff theorem in some sense when treating this kind of nonlinearity. So just to mention some paper, in the case in 1986, Drabek and Dieter treats the case of a non-resonance, the resonance rectangle, which is indeed non-resonant. So we can see that in some sense the rectangle mu that we have seen before, this one, does not intersect the Dancer-Fuќc curve that you can see drawn in blue, colored in blue. And so in this case, you can find the solution. Then in 93, Fabry-Avest treats the case of an infinite rectangle. So you have to imagine that you do not touch the spectrum in this part of the rectangle, and then you go to infinity and you are on the left with respect to the asymptote of this curve. This curve has a vertical and horizontal asymptote. And so this is a non-resonance situation if you ask that this vertical line, the right side of the rectangle, is not the asymptote. If you touch the asymptote, it's quite dangerous. You have to introduce maybe an Landesman and Lazer condition, for example. And the double resonance situation arises when the rectangle touches two subsequent lines. So in this point, clearly because of the shape of the Dancer-Fuќc spectrum, you cannot touch this with this point, the line not, diciamo, crossing it in many points. So the resonance situation, when you can try to find periodic solution, is when you touch with the vertex, the curves in some sense. So if you look to the bibliography in 1990, Fabry and Fonda treated the symmetric case. So the nonlinearities, both at plus infinity and minus infinity, are say between two subsequent eigenvalues of the symmetric oscillator, harmonic oscillator, the classical one. And Fabry in 95 generalizes such a situation to asymmetric nonlinearities, treating a resonant rectangle, say, with these vertices touching the Dancer-Fuќc spectrum, and introduce a double Landesman and Lazer condition. So the question we are going to treat is what happens when this red rectangle goes to infinity. So imagine that these 2 points goes to infinity. And so in some sense, you are in the asymptotes, and the full rectangle goes to plus infinity. Let me emphasize that the double resonant situation where this, for example, if we enlarge this green rectangle and we admit that this vertex touches this line and this vertex at infinity touches the asymptotes, is not present at the moment in literature, the existence result for this problem. But there exists this one because I have written it. And so we will see this situation in what follows. So how can we interpret such a situation? We have three possibilities. The first one is clearly the one-sided superlinearity. So we ask an asymptotically linear growth between the value of the two asymptotes, and then a superlinear situation at minus infinity. And this case is quite immediate to be considered. So you simply need to change this constant with infinity. Another non-trivial situation is the case of strong repulsive singularity, where you consider a singularity. So the differential equation is defined for positive s, and at zero you have a nonlinearity which behaves in this way. So it is controlled from above by a function which goes to minus infinity, and having an infinite energy. So you need an infinite energy to reach the singularity. So, and this is the case of a strong repulsive singularity. These two cases are very similar when you play with phase plane analysis. So the ones of you which are habituated, used to work with phase plane analysis, understand easily the fact that when you are near the repulsive singularity, you go in some sense very fast in the phase plane, as you go very fast when you want to go to minus infinity when you have a one-sided superlinearity. So these are the very similar situation that can be treated in easily in the same way, easily in the sense that if you can write a paper in this situation, it is reasonable that you can write a paper in this setting, in some sense, very just saying very roughly this thing. Another situation is the impact oscillator. So you have the differential equation, which is defined for positive x, and you ask some impact condition on the line x equal to 0. And so this is another possibility. So just to add other possible, to enlarge the previous bibliography, I want to list some situation treating the case of strong singularity or impact oscillator. And as you can see, I have highlighted in red this paper because it's the one that suggests me this research I am going to expose. This is the Landesman and Lazer condition introduced by Fabry in '95. What is a Landesman and Lazer condition? In some sense, we can explain it in this way. So it is a sign condition, and if we consider the resonance rectangle given here, the one of Fabry, you can see these 2 points. This is the point mu1, nu1. This is the point nu2, mu2, and you can see, since we are on the Dancer-Fuۂc spectrum, that there are non-trivial solutions for the asymmetric oscillator. So we need to consider all the solutions of these two asymmetric oscillators. So we take these solutions and we require this assumption. The term you see in red is in some sense a remainder. The difference between the nonlinearity and the linear part of the asymmetric oscillator. In some sense, you require that there is some kind of pushing. If we look to the picture, sorry for going along the pages so fastly. So, and in some sense, this condition push the vertices in some sense inside between the two curves. In some sense, if you have a solution, then in reality, the solution in some sense does not remain on the dangerous zone. So you ask this sign condition. And what happens when nu goes to infinity? So roughly speaking, we are going to see, just a moment, please. So what happens when we go to plus infinity? So we consider 2 points on the Dancer-Fuۂc spectrum. Imagine that here you have the rectangle, the resonance rectangle, and this is the vertex that you are considering. So if we consider, if we consider this point going to plus infinity, we can see that the humps of the positive humps enlarge and the negative ones reduces and goes to 0. And the solution seems to be the one of the impact oscillator. As you can see, this vanishes, and you think that when nu goes to plus infinity, it's reasonable to ask a Landesman and Lazer condition involving the solution, the impact harmonic oscillator. And so this is what can be done. And so we can, for example, replace just if we put here infinity, you can notice from the previous animation that this part, it's not important, vanishes in some sense. The set goes to zero, have a zero measure when you pass to the limit. So you think that this part will disappear in the condition. And in some sense, this part remains. And so the natural Landesman and Lazer condition that you expect in this situation is something like this. You consider the solution of the impact oscillator, the absolute value of the sign, and you try to substitute it with and also all the other solutions that you can obtain by translating it. And you ask such a condition, the first and the second Landesman and Lazer condition. This is what you expect, but it is not enough. This is briefly the result presented by Fonda and Garione in 2012 in the singularity case. So we have a singularity, and they ask no resonance on the left. This is due, I think, because the phase plane analysis on the left, in some sense, is very presents some additional difficulty. On the right, you can find the resonance situation. So let's just focus the attention on the fact that here you do not find a lim-sup condition. This is due because when you consider the remainder between the difference between f and this linear term, if you ask to have a function, say, s of tx, which is sublinear with respect to x, you have some problem when you want to apply Fatou lemma in the proof. So you need to ask some additional assumption. And this situation is well explained in this paper by Boscagini and Garione, where they analyze this situation when you do not have a constant control between this difference in some sense. And so this is the reason for which you will find in the following part this kind of inequalities and not this one. Because if you ask this inequality, you need to add some ad hoc conditions, say, and some strange technical hypotheses, say, not easy to be read. So I maintain we consider this situation for simple. And if you look to the result, you find that Fonda and Garione use another test function for the Landesman and Lazer condition, not the expected one, but a different. The difference is essentially that these functions as this graph, and this function as this graph. So you have only one hand, and then it goes to zero. Then you have a translation, so clearly you can consider also the other humps in some sense. And so in this situation, the Landesman and Lazer condition they introduce is stronger than the expected ones, because in some sense, if Landesman and Lazer condition of tilde type is guaranteed, then you can prove that the Landesman and Lazer condition the expected Landesman and Lazer condition hold. And so in some sense, this condition is stronger than the expected one. So let me give you the sketch of the proof. Very, very simple. I do not enter in detail. So as usual, you apply topological degree theory, and we want to an a priori bound in order to apply the homotopy invariance of the topological degree. And so you argue about contradiction and assume the existence of a divergent sequence. Then what you do, you normalize the sequence, and then by some compactness argument, you can say that there exists a subsequence converging to a certain limit. Then you must do some phase plane analysis, and you can say that the limit solves a certain kind of impact oscillator type equation. But the problem is that it is quite difficult to ensure that the impact is elastic. What I mean that if you make phase plane analysis, let me here write the case of superlinearity, the orbit goes in this way, and you need to ensure that if you enter here at height minus epsilon, you want to exit at height plus epsilon, just or plus something small. You want, in some sense, a control between this point and this point. And this condition is not easy to be obtained for a general nonlinearity. So this is the reason for which in the result by Fontengarione, you find in some sense the strong Landesman and Lazer condition with the function, with the tilde functions, say this one. Okay, so we can say that in some sense the difficulty is hidden here, but also here. So if the problem is the impact, why do not treat the situation of an impact oscillator where the impact is guaranteed, of course? So inspired by a paper by Bonner and Fabry in 2002, I consider this situation. So I ask the nonlinearity to be between two asymptotes of the Dancer-Fuۂc spectrum. And I add the bouncing condition introduced by Bonner and Fabry in their paper, where essentially I say that I can bounce elastically, but I can land on the surface on zero with a zero velocity, or I can take off. So this is not a pure impact condition that, as you can see in some paper by Ortega, Torres, and where essentially you can see the use of successor map, and you can count the bouncing. Because in that paper, you have to introduce some condition at zero. Here, you do not have any condition at zero. So you have only asymptotic condition. So you can introduce the expected, the Landesman and Lazer condition, and you can find the periodic solution that you expect. But there's a problem. You cannot ensure that this solution is not the trivial one. You can. This is guaranteed that if F is well done, in some sense, if there is a sort of wind that pushes away the solution from x equal to zero, so some sign condition at zero. And this factor was underlined also by Bonner and Fabry in that paper, surely, that this possibility can arise. So, but if you ask, for example, that the functions is negative sometimes when x is equal to zero, then the trivial solution cannot be a solution of this problem. And so the solution you find is not the trivial one. Otherwise, you can treat also, and so just to make some, this is the reference for the paper of the impact oscillator, which appears in 2017. And 1 year before, but it was written later. It is just for editorial reason that here you can find the 16 because it appears online first. So this is the previous year. And on Analisi Matematica Pura Applicata, here I have discussed the situation of the problem with singularity and the problem of a superlinear case. So you can change, you can choose which approach you desire. But you have to pay with the strange assumptions. This is very strange, but don't read it. It is not essential. In some sense, this assumption requires that the dominant term is the same at every time. You can see the positive example and the negative example gives that your nonlinearity at a certain time, t equal to 0, is not ruled by x to the 5th power, but x to the 3rd power. So this nonlinearity does not satisfy H. It is only at this point, the vanishing point. And so this is good, and this is not good. So what can you ask? If H holds, so if the strange hypothesis holds, so in particular, if the dominant term of the nonlinearity is the same at any time in some sense, then you can use the better, the weaker in the sense that you ask less. So it is a stronger result. The weaker Landesman and Lazer condition with the expected test function and gain the T-periodic solution. If H does not hold, you can't. You cannot guarantee this kind of perfect elastic bounce condition when you consider the divergent sequences. In some sense, the perfect elastic bounce is hidden in this one, in some sense. This is the perfectly elastic bounce property. So this is some ad hoc condition, say, in order to give this possibility. So if H does not hold, you have to pay with a strong Landesman and Lazer condition with a wrong test function in some sense, and you can reach the double resonance result. So let me underline that the paper by Fonda and Garione give an idea of what can you do with this Landesman and Lazer condition. This is new in any case, and certainly this is the previous one was the better one. So oops, what happens? Just sorry, the arrows on my keyboard doesn't work well. So if you ask this, also you can improve their theorem on both sides. So this is all, and the result you can obtain. And the problem is that the first operant problem is if it is possible to renounce, to cancel the H hypothesis and use the good, the expected text function also when H does not hold. I don't know, I have no example in which H does not hold, and so there are no counterexample to this theorem. So maybe H, maybe not necessary, I don't know. Another open problem that I have stated previously is this case when you consider the unbounded rectangle touching here and touching the asymptotes. So this situation. This is not present in literature. And I suspect that in this case, certainly H does not hold because you have asymptotically linear growth on this part, and then in here not. So H does not hold in this situation. And so it is an open problem on how to write the double Landesman Lazer, the Landesman Lazer condition in this situation. So another problem that can be treated is the fact that you can consider some time-dependent lim-in-flim sup condition and try to understand what can you do in this situation. And just in order to conclude, let me spend a few words on Sturm-Liouville boundary value problems. And you can see this is these are some paper written in the setting of positively homogeneous of degree 2 systems, the ones that are written in this way, and perturbations that Alessandro Fonda mentioned previously in his seminar. And here you can find the case of non-resonance, say this dot resonance, the point resonance, if you consider the Dancer-Fuۂc spectrum, is the case when you have the rectangle is a point in some sense. And then I have written a generalization to rectangles in some sense, and introducing Landesman and Lazer condition. So just a forthcoming investigation with my master degree thesis student, Rossella Marvulli, we are treating the Neumann problem. So we are translating, in some sense, the result for the periodic problem into the setting of the Neumann problem, which as those of you that are used to play with Neumann and periodic as a similar problem, that it is quite surprising the structure of the Neumann solution of the impact oscillator. What you expect to have? So it is not so trivial. It is quite surprising, but we hope to give you a written result as soon as possible. And let me conclude with a very small bibliography on the recent result involving this kind of problem. And thank you for your attention.
Thank you very much.